crystal field stabilization energy. So now see CFT is crystal field splitting is nothing but see whenever you are having free metal ion, so at that time there is a no splitting. But when you can have a ligand which is approaches to metal, when ligand come close to the metal, so at that time you can have a crystal field splitting. So the crystal field theory is basically on the basis of a breakdown of degeneracy. So this theory was given by scientists Bethe and Van Vleck. This theory CFT is given by Bethe and Van Vleck. And Penny, Bethe, Van Vleck and Penny also. So see, this theory is basically it is there is the electrostatic force of attraction between, that is repulsion is a one kind of electrostatic force of attraction. So between ligand and central metal atom. So that is one kind of the ionic bonding. So it is based on electrostatic force of attraction between central metal atom and ligands. So you are getting splitting of various d orbitals take place. So we know that see this d orbital is split into two set. So initially say whenever metal is in a free state, so at that time all 5 orbitals having same energy. But once it is come in close to ligand or if complex is formed, so in a spherical field you can have a repulsion, and that's why this 5d orbital gets split into two different levels. One set is you can say Eg, that is having 2 orbital, where its energy increases by 3/5 octahedral, or you can say it is by 6 dq. And second one is nothing but P2G set of orbital, where its energy decreases by 4 dq. If you write down its value, then it is a 4 dq. So this is increases by 6 dq. You can have a here. It's a 6 dq and another one is 4 dq. This is increases by 6 dq. This is by 4 dq. And this is by 6 dq value. Why this pen is not working properly? So this is by sin, so it is by 6 dq and this is by 4 dq. So you can have a say total value difference is 10 dq between these two lines. Okay, so now see, so here the reason for increasing in such energy is only the, you can have a here see on lobes of this orbital are along the axis, and that's why it experiences more repulsion, and because of the more repulsion you can have more energy for particular orbitals, and those orbitals in which lobes are away from or in between the axis at that time it having less energy. So here x square minus y square and z square orbital, which its lobes are along the axis, and therefore ligands and orbitals are on the same axis, so they are very close. So they experience more repulsion as compared to bxy, dyz, and dxz. We have also checked the crystal field stabilization energy for particular configuration in this, and see this is the electrochemical series where you can decide whether given complex is high spin or it is low spin. Now this is the way you can fill up the electron in octahedral field, and few examples to calculate CFSC. So this is we have completed yesterday, and tetrahedral complex, that is here lobes are in between axes. So dx square and minus y square and dz square orbitals are away from ligands, and that's why set of e orbitals having its energy decreases, whereas set of t2 orbital which having that energy increases. And of course octahedral splitting is more as compared to tetrahedral. So these things we have completed. Now what happens in the tetrahedral complex? See, tetrahedral complex, all are the high spin complex. Remember, all tetrahedral complex are always high spin. That means there is no pairing of electron. You cannot have a pairing of electron in the case of the tetrahedral complex, and that's why you can have all the electrons in a tetrahedral complex, they are always remains unpaired, because here this pairing is not take place. Tetrahedral complex is concerned, so there is no pairing. So what happens here? See, you can have the splitting energy, tetrahedral splitting energy is less than the pairing energy. Tetrahedral splitting energy is less than pairing energy, and therefore no pairing of electron take place. Okay, here pairing is not possible, and therefore there is no pairing of electron. As a result, this complex is, you can say, high spin complex. But the same case is the opposite in the case of octahedral complex. If pairing energy is less than splitting energy, then you can have a pairing. In the case of octahedral complexes, what happens? Is a electrochemical series. So here what happens if pairing energy is, if octahedral splitting energy is greater than pairing energy, so at that time you can have a pairing of electron take place. So that complex, you can say it is strong field complex. It's greater than pairing energy. So pairing of electron take place. As a result, what happens? If electron gets paired, so complex is called low spin complex. And that is possible with strong field ligand. But if pairing energy is greater than octahedral splitting, then no pairing of electron. At that time, see this complex is, you can say it is high spin. High spin complex, electron may remains unpaired. So that is there. So that's why see here tetrahedral complex are always high spin complex. So there is no pairing and that's why you can have a, say, suppose D1 configuration. Then how electron gets arranged? So which orbital fill first?
T2G.
See, E and T2G, where E set having more energy as compared to T2 in case of tetrahedral. So lowest energy orbital fill first. Look at here. E orbital having C lower energy as compared to T2. And that's why E set is filled first. See, it is not a, see here we cannot mention symmetry because here there is no case of Girard and un-Girard because there is no center of symmetry with tetrahedral configuration. So one electron is entering into E. If you, and it is a high spin, complex is a high spin, whether ligand is strong or weak. Tetrahedral geometry always it is high spin complex. So see, if you having D2, then again 2 electron gets accommodated into E orbital and T2 orbital remains as it is. What's about you can say D3. So third electron gets enter into
T2.
T2. Good. So it is enter into T2 set of orbital. So maximum you can have a say 5 and per electron. If you go for D5, then this become 2 here and 3 in T2 orbital. If you having D6, then now pairing is take place from E set in this way. If you go for D8 configuration, so what happens? 3 pair are there. Okay, so in this way pairing is take place. So if you calculate crystal field stabilization energy for D1, so it has 1 electron multiply with its energy decreases by 6 dq. And T2 with 4 energy increases by 4 dq, but T2 is already having 0 electron, so 0 multiply with 4 dq, so it's a 0 and there is no any electron pair, so your answer become minus 6 dq. What's about crystal field stabilization energy for D2? It's a 2 into minus 6 dq. So what is its answer? Minus 12 dq. What's about D3? 2 into minus 6 dq plus 1 electron is in T2 multiply with 4 dq. Its energy increases by 4 dq. So your answer become minus 8 dq. What's about in D5? What is crystal field stabilization energy?
0.
0.
Yes, 2 into minus 6 dq because orbital is symmetrically filled. So again 3 into minus 4 dq. So it become you can say 12 plus and 12 minus. So it becomes 0. Good. If with 6 dq is concerned, so crystal field stabilization energy is equal to 3 into minus 6 dq plus 3 into my plus 4 dq
Minus 6 dq.
plus 1 electron pair. So your answer become minus 18 plus 12, that is minus 6 dq plus 1 p. For D8 is concerned, so 4 into minus 6 dq, that is 24 plus 4 into plus 4 dq, that is 16 plus 3p. So your answer become 24 minus 16 minus 24 plus 16.
Minus 8
That is
dq plus 2.
minus 8 dq plus 3p. So in this way, you can do the calculation for calculation of crystal field splitting. If you having see any configuration like MnO4 minus KMnO4, or you can say MnO4 minus 1. So here see this is a tetrahedral geometry. What is Mn? What is its atomic number? Mn
M7
having
plus
atomic number is Mn plus 7. So it's a 4s2 3d 3d7. It's the electronic configuration of Mn 3d5. Sorry. So if you're having plus 7, then it is D0. Okay, so CFSC become 0. But what's about cobalt H2O 4 times? Or you can have a nickel NiCl4 minus 2. So here oxidation state of nickel is X minus
plus 2.
4 is equal to minus 2. So X is equal to plus 2. So it's a nickel plus 2. It's a D8 system.
D7.
So in a D8, 28 atomic number with nickel. So 8 electrons are arranged in this way. These are the 5 electrons. Okay. Then this is a 6, 7, and 8. So already we have calculated crystal field stabilization energy is equal to 4 into minus 6 dq plus 4 into 3 dq. Sorry, 4 dq. So it is a 16. Already we have do this calculation plus 3p. That is your answer become minus 8 dq plus 3p. Okay, so for complex you can do same calculation. Now see tetragonal distortion from octahedral geometry, or you can say crystal field splitting in tetragonal geometry. What happens after then say next we go for tetrahedral tetragonal splitting, or you can say distortion in a octahedral geometry. So what happens is normally this is your z-axis. Now this is z-axis and this is you can say x-axis and this is y. So this is the normal octahedral geometry. Now ligand interact with orbital present on the axis here in this case. So you know that what is splitting. So in this case the splitting become like to octahedral splitting. These are the 5d orbitals. These are splitted into two sets, EG and T2G. This is the case of you can say octahedral complex, octahedral geometry, ML6 type complex. This is the way orbital gets splitted. So now then what happens, see, in the tetragonal complex, there is a elongation along z-axis. See, this is a normal z-axis, but now see such elongation is there. That is
Z in and Z out.
yes, it is called on-Taylor distortion also. That is called Z in and Z out. Z out means increasing in bond length along z-axis, and Z in means decreasing in the bond length. So it is called tetragonal elongation. So in a tetragonal complex, what happens? Elongation of z-axis take place.
Unsymmetrical this electron distribution in EG orbital.
Yes, elongation of z-axis. As a result, here see ligand is there. Here is ligand is there. Now you tell me ligand is go away from metal or it is come close to metal?
Go away from metal.
It is go away
Z-axis.
from metal. So what's about repulsion between metal and ligand? It is increases or decreases?
Z-axis increases. Z-axis.
See, this is your normal 5d orbitals, okay, in a free metal ion state. This is in a free metal ion. Now then what happens? See, it is splitted into two set in octahedral, that is called T2G and EG set. And why this is splitted? Because there is a repulsion electrostatic force of attraction, or you can say repulsion of metal electron with ligand electron. So energy of this set is increases dx square minus y square, and dz square is increases, and you can have a see this 3 orbital where energy is dxy, dyz, and dxz is decreases. So this is happens from barycenter. Now the question is, see here ligand goes away, so negative charge on ligand and negative electrons of metal both are repel with each other, so that repulsion is increases or decreases?
Decreases.
It is decreases, because ligand go away. If it is close, then you are having more repulsion, but if it is goes away, then repulsion is decreases, and if repulsion is decreases, then energy is also decreases. Okay, so what's about energy of jet component? It is increases or decreases?
Decreases.
So this will undergo see further splitting here out of these two orbital. In the case of tetragonal, the energy, this is a case of octahedral, but in the case of tetragonal geometry, tetragonal elongation, energy of z orbital is increases, decreases, and energy of dx square minus y square orbital is, and energy of you can say z orbital is decreases. Similar way, see here it is take place, energy of dxy is increases, and which two orbital it is decreases?
XZ and YZ.
Yes, it is decreases with dxz and dyz, it is decreases. So z component, its energy decreases. So this is called tetragonal elongation. Dxz and dyz, z component is decreases. So this is called, this is take place in, so see this is a case of tetragonal complexes. This is we call tetragonal complex. Tetragonal complex. Again, see if you going to remove two electrons, two components, that is you can say Z, so you may got square planar geometry also. See this is, look at here. See this is your normal octahedral. This is your normal octahedral case where energy of EG set is greater than that of T2G. Here energy of EG set is greater than T2G. And this is a tetragonal case
And square planar. Next.
where yes, where the x square minus y square having more energy as compared to z square here also. Now then see this is the case of square planar geometry. In the case of square planar, what happens if you remove these two z ligands? So see here you can have a see dx square minus y square having x component is only there. Okay, so x component having more energy, then z component is comes next. So this is, you can say it is a splitting in a square planar complex where only x and y axis experience more repulsion. There is no repulsion on z axis, so therefore x and y component shows more energy as compared to z component. Okay, so this is exactly the splitting. The first one is octahedral. Of course, energy gap is of 10 dq. Then you can have a tetragonal distortion, and then you can have a octahedral splitting. So look at here. So now you can compare see all this splitting. So you know very well which splitting is more, which value is greater.
Square planar.
Square planar, yes. Square planar splitting is of highest value. If you compare all these three, then definitely the value of square planar splitting is more as compared to octahedral and tetragonal, all this. Okay, next is tetragonal. Then what's about next?
Octahedral.
Then it is octahedral. Then it is tetrahedral. So tetrahedral comes last. In a square planar, what is order? In a square planar, order become
X
dx
square,
square minus y square, yes. Then
xy,
dxy
then dt square,
followed by dx z square,
then dxz and yz.
dz and dyz. This is the order. In the case of tetragonal,
X
dx square minus y square, then
d square,
dz square followed by dxy,
then
then
yz,
dyz and
xz.
dxz. So this is the order. So in the square planar complexes, you can have a energy of a particular x component is only higher because all these spin which are on direction of x and y. And tetragonal complex is concerned, then it may be, if we consider the case of elongation, so that's why z component having more energy as compared to you can say x and y. So see, this is about crystal field splitting. So crystal field splitting is basically arising between central atom and donor ligand. There is a repulsion between these two, and that's why crystal field splitting is arises. We have also see calculated 10 dq value. So now see how to getting crystal field stabilization energy, which factor which will affect on crystal field splitting, we go for that. Okay, so before starting that, so this is electrochemical series. That is nothing but arrangement of ligand according to, you can say, decreasing order of their field strength. So up to here, up to water molecule, these are the weak ligand in this series. This is a weak ligand, and from NCS onwards, these are the strong ligand. Okay, so if ligand is strong, then there will be pairing. If ligand is weak, then there is no pairing. So see, this is a series which is very important, that is called electrochemical. And now this is just a special series that is called Naphthalogetic series. Term Naphthalogetic means cloud expanding. The idea is that basically comes from more covalent ML bonding. The more unpaired electron of the metal are spread out over the ligand, and lower is the energy required to spin pair these electrons. So largest, see, F minus has largest P values. That is called pairing energy is more, then electron may remains. See what happens in the pairing energy. We have also seen that if pairing energy is more, here that is mentioned over here. If pairing energy is more, then electron may remain unpaired. No pairing of electrons take place. Okay, so electron remains unpaired. So same concept is utilized here. Largest P means electron remains unpaired. Okay, so in this way you have to see arrange the different ligand in a series. So, and another factor is covalent bonding. So spectrochemical series basically indicate how delta is varies for any metals ions as the ligand set the changes, or you can say as the ligand sets gets changed. It may be weak ligand or strong ligand. So that is basically on the same. On same way, you can have a see whether sometimes spin pairing is take place or sometimes electron may remain unpaired. So manner in which spin pairing energy is varies is called Naphthalogetic series. This series is based on the pairing energy, see remember. And spectrochemical series is based on the field strength. So F minus having higher pairing energy, and therefore it is written first. Then H2O is there. Okay, then NH3 is there. So term Naphthalogetic means cloud expanding, or you can say idea is that the more covalent ML bonding, more the unpaired electrons of metal are spread out over ligand, and lower is its energy required to spin pair this electron. So now see on basis of this, what are the applications of CFT? So see, CFT is a very useful to calculate 10 DQ, or you can say DQ value. So crystal field stabilization energy, that is called 10 DQ value, is depends on what? Which are the factor which will affect on 10 DQ? So 10 DQ value, or you can say splitting energy value, depends on, basically
Metal or
it is yes,
metal
basically
oxide
it is
state.
between, it is basically between repulsion between metal and ligand. So first is geometry of the complex. We take as a various factor. The first one is geometry of complex.
सर एक बार लास्ट स्लाइड में लास्ट लाइन समझा दीजिएगा.
Okay. See, Naphthalogetic, basically it is a see, repulsive factor, you can say. So Naphthalogetic means cloud expanding. Idea is that more covalent ML bonding, more will be unpaired electron of the metal are spread out over the ligands. तो बेसिकली क्या है, जिसकी सी पेयरिंग एनर्जी ज्यादा होगी उस केस में इलेक्ट्रॉन अनपेड रहेंगे, और इलेक्ट्रॉन अनपेड रहेंगे तो वो एक क्लाउड की तरह मेटल के आसपास ज्यादा स्प्रेड होंगे. ओके, एंड दिस इज द रीजन. ज्यादा इलेक्ट्रॉन है तो ऑर्बिटल और रिपल्जन कैसा होगा मेटल और लिगेंड के बीच में?
ये सर क्लाउड ज़्यादा रहेगा.
हाँ, ज्यादा रहेगा तो रिपल्जन मोर रहेगा. सो रिपल्जन ज्यादा है तो एनर्जी क्या होगी? डिक्रीज.
Increase.
So therefore energy gap is, energy is decreases, so lower is the energy required to spin pair this electron. इसलिए
सर मतलब मोर द नंबर ऑफ लोन पेयर भी तो कह सकते हैं. मोर द नंबर ऑफ लोन पेयर मोर विल बी द क्लाउड एक्सपेंडिंग.
more the number of lone pair नहीं, more the number of unpaired electron. पेयरिंग नहीं, अनपेड, फ्री इलेक्ट्रॉन.
ओके सर.
है ना, जितने ज्यादा फ्री इलेक्ट्रॉन होगा उतना ज्यादा क्लाउड होगा, उतना वो रिपल्सन ज्यादा रहेगा मेटल के साथ, उतनी उस ऑर्बिटल की एनर्जी ज्यादा रहेगी. इसलिए आपकी जो क्रिस्टल फिल्ड स्टेबिलाईजेशन एनर्जी है वो अब कम देनी पड़ेगी. लोअर इज द एनर्जी रिक्वायर्ड टू स्पिन पेयर. उनको पेयरिंग करने के लिए कम एनर्जी, क्योंकि ये बेसिकली CFT और 10 DQ इज ए, you can say it's a negative value. Okay, so क्रिस्टल स्टेबिलाईजेशन के लिए कितनी एनर्जी जरूरी है वो इंडिकेट करता है. उतना वो इम्पोर्टेंट नहीं, बट इट इज स्लाइट, इट इज ऑलमोस्ट सिमिलर टू केमिकल इलेक्ट्रोकेमिकल सीरीज, बट एक है वो लिगेंड फील्ड स्ट्रेंथ के पे डिपेंड है और दूसरी है वो पेयरिंग एनर्जी पे. उतना ही डिफरेंस है. So see geometry of complex, how it is affect. So you know very well tetrahedral geometry having more energy as compared to, sorry, less energy as compared to octahedral, and octahedral geometry having more energy as compared to square planar and tetragonal. This is having, so octahedral having more energy as compared to tetrahedral. Tetrahedral having, and then octahedral complex having less energy as compared to tetragonal, and highest energy is exhibited by square planar. So you can see that if geometry is changed, crystal field stabilization energy is changed. This is a relationship. Tetrahedral and octahedral are related by this formula. That is nothing but 0.44 octahedral splitting.
Sir, what is for cubic?
Splitting for cubic geometry?
Yes, sir.
I think cubic is not there in our syllabus and that's why I have not covered. अदरवाइज उनके लिए भी आपको जैसे प्रिज्मेट टाइप ज्योमेट्री ऐसी तरह आप क्रिस्टल फिल स्प्लिटिंग उनके लिए भी सेपरेट और प्रिज्मेट ज्योमेट्री भी है, तो आप ये भी लिख सकते हो ऑर्डर, बट आपके जो सिलेबस में नहीं है ना, इसलिए मैंने इसको अवॉइड किया है, जैसे एबीपीटी भी नहीं है.
Okay, sir.
Okay, otherwise you can see if you want to just memorize energy order, then you can remember this the energy order for particular axis in the case of cube. क्यूब में भी सिंपली क्या है, सिंपल क्यूब है आपके पास, तो T2 सेट है उनकी एनर्जी कम रहेगी, ई सेट की ज्यादा रहेगी, दूसरा कुछ उसमें नहीं है. So basically cubic geometry is this type. जैसे आपके पास एक सिंपल क्यूब है सपोज, this is a cube. So what happens in this case? So see, whatever 5 orbital is there, again see this is a cube, so cube is, you know very well, here two set having more energy, that is called Eg, and T2 having lower energy, like to octahedral. उसमें कोई नई चीज नहीं हो, यहाँ पे भी -4 dq आ जाएगा, यहाँ पे 6 dq. Okay, because basically see octahedral geometry is similar to cubic geometry. वैसे तरह आप, सॉरी इसमें थोड़ा अपोजिट आएगा, इसमें तरह आप कंसिडर कर सकते हो, ई सेट की एनर्जी है वो कम रहेगी और T2G सेट की ज्यादा रहेगी क्यूबिक में, ये अपोजिट हो जाएगा. बाकी सब सेम है, ऑक्टाहेड्रल एंड क्यूबिक दोनों सेम ही है, बट थोड़ा ये ऑर्डर रिवर्स हो जाएगा. यहाँ पे 3 आ जाएगा, दैट इज T2 सेट, एंड यहाँ पे EG सेट, दैट इज TZ स्क्वायर माइनस, ये आपको ऑर्डर एग्जाम्स के लिए याद रखना है तो आप रख सकते हो, कोई कॉम्पिटिटिव एग्जाम्स के लिए, XY DYZ एंड DXZ. ओके, उसमें क्या था, यहाँ पे 2 और लिगेंड्स थे ऊपर, तो वो एग्जैक्टली ऑन द एक्सिस आ रहे थे उसमें, बट यहाँ पे ऐसी इन ऑक्टाहेड्रल के केस में, बट इन केस ऑफ क्यूबिक ज्योमेट्री, सो यू कैन हैव ए सिंपल, दिस इज अ डायग्राम वेयर x square minus y square and z square orbitals are lies in between the axis type, like whatever you have written in the case of tetragonal. टेट्रागोनल में ऐसे क्यूब ड्रॉ करके लिखा था ना हमने, यहाँ पे मिडिल में ज्योमेट्री ड्रॉ करके ऐसी तरह, बट यहाँ पे आपको ऐसी तरह स्प्लिटिंग रहेगा क्यूब में. क्यूबिक क्रिस्टल फिल स्प्लिटिंग इज सिमिलर टू टेट्रागोनल टाइप, opposite to octahedral type. But I think this is not there in your syllabus and that's why I have not taken. Otherwise, for various geometry like anti-prismate or this geometry, you can have a different splitting. Okay, so
Yes, sir.
now, so this is a first factor, and the square planar splitting is equal to, what is the relationship between square planar and you can say octahedral? So that is square planar splitting is equal to 1.33 octahedral. So see, this is a relationship. Second factor is it is depending on nature of ligand. Crystal field stabilization energy is depending on nature of ligand and nature of central atom also. So first write down the nature of central atoms, that is you have already told that atomic number and all these things. Nature of central atom. So here what you can do, see, you can have a central, that is the nature of central atom is, here you can look at 4 principal quantum number first. Principal quantum number is increases N is increases, then splitting energy is also increases, and that's why for 3D orbital it is having lower energy as compared to 4D. 4D having lower energy as compared to 5D. The principal quantum number increases, crystal field stabilization energy is also increases. If you take an example of Fe plus 2, that is D6, it's a D6 configuration. You can have an example of ruthenium plus 2. And you can have a osmium plus 2. So see, Fe is from 3D, this is from 4D, and this is from 5D series. So therefore, in all this case, N is increases, so delta is also increases. But if you go for, so similar, you can have another example also. You can have a cobalt plus 2 compared with the rhenium plus 2. It is compared with iridium plus 2. So if you come down, then N is increases. So crystal field stabilization energy is also increases. So that is principal quantum number. Second one is the oxidation state. Very, very important factor is nature of central atom. उसमें आएगा oxidation state. हेलो हेलो फोन करो मैं थोड़ी देर में करूँ. Oxidation state. See, second one is oxidation state of metal. That is what happens in the case of oxidation state. See here, oxidation state is suppose plus 2. Then this is a distance between ligand and metal. And if oxidation state you can increase, that is plus 3. So this is a attraction force between these two. So what happens if you increase oxidation state? Then what's about attraction?
Attraction will be increases.
Yes, attraction between metal and ligand is increases. What's about repulsion? Repulsion is also increases. Repulsion, that is repulsion of electrons of metal with electrons of ligand. Metal जैसे ही ये नजदीक आएगी metal की ligand, so repulsion भी increase होगा. Repulsion is also increases. ये attraction है ना, वो it is between positive charge of metal and ligand, और repulsion है वो ligand के इलेक्ट्रॉन और metal के इलेक्ट्रॉन के बीच में है. So as the oxidation state is increases, so distance is decreases. See, distance between metal and ligand is decreases, and as a result, what happens? Crystal field stabilization energy is increases. Yes, if you go from this side, oxidation state is increases. So all this thing is happens. So see, oxidation state is directly proportional to crystal field stabilization energy. Okay, then see, after that nature of metal, then third one is number of d electrons. Third one is oxidation state of metal, then number of d electrons. Electrons which are there in d orbital. So as the number of d electrons increases, crystal field splitting increases. So the crystal field splitting is decreases. This is decreases. Because see, metal oxidation state you can keep constant M+2. And if you just change the electrons, what happens? See, ligands with if less electron, so repulsion is less. We are talking about in ND cells, in a same cell. Number of d electron is increases. So as a result, distance is also increases, repulsion is decreases. Number of d electrons, it is orbitals go away from nucleus. So number of d electron increases, attraction decreases. Repulsion distance increases. Repulsion decreases. So crystal field stabilization energy is also decreases. किसकी बात करें हम इलेक्ट्रॉन की मेटल के इलेक्ट्रॉन ओके मेटल के इलेक्ट्रॉन जितना ज्यादा होगा उतना लिगेंड है वो उनसे दूर जाएगा ओके सो बिकॉज लिगेंड के इलेक्ट्रॉन ज्यादा है तो अलग बात है सी मेटल के इलेक्ट्रॉन ज्यादा होगा सो रिपल्जन इज ultimately ligand goes away so repulsion is decreases so this is about nature of metal is it clear
Yes, sir.
okay now we go for nature of ligand that is another very important factor that is number 3 is nature of ligand so here see you can have an electrochemical series okay if strong field ligand is there so more will be the splitting weak field ligand is there so less will be the splitting so next is nature of ligand that is ligand field so you can have as ligands are in an increasing order of their field strength so crystal field stabilization energy is okay directly increases when you so you can go for spectrochemical series it is increasing order of field strength strong field ligand more crystal field splitting so strong field ligand more CFSC weak field ligand is there so its value is less crystal field stabilization energy see here it is value is CFSC is either negative or zero it is never positive remember हमने सारे calculations देखे थे so in that case it is either negative or zero it is never positive okay सारे calculations देखे थे so CFSC is associated with thermodynamic crystal field stabilization energy is associated with with thermodynamic stability of complex. It is associated with the thermodynamic stability. Higher the crystal field stabilization energy, more will be the stability of the system. Higher the CFSC, crystal field stabilization energy, more will be the thermodynamic stability of the system. बस जितनी वैल्यू ज़्यादा होगी उतना ही स्टेबलाइजेशन जो है वो ज़्यादा होगा. And value is negative or it may be 0, but it is never positive. For completely filled and half filled configuration, it is 0. For half filled and completely filled configuration, CFSC is 0. It's a 0 value. So that is we have already calculated. We already see the case of D5. So you can have a D5 or D10. It is 0. So maximum value is for which case? Can you say me in which case you are getting maximum value by looking all this calculation? This is the case of high spin complex. You can go for low spin octahedral. This is the low spin octahedral. Remember, see, you can calculate, you can do calculation of crystal field stabilization energy for D6. So D6 octahedral, what happens? In the case of D6 octahedral, you can have a, suppose strong field ligand is there, then electron gets paired in T2G. Easy orbital is vacant. So maximum crystal field stabilization energy you are getting in this configuration. 6 minus 4dq
plus 3p
plus 0, okay, plus 3p. So you are getting minus 24dq plus 3p. So see, this is the maximum value. So therefore you can say that CFSC is maximum for D6 configuration, it is maximum, and for D10 it is 0. For half fill D5 and D10 it is minimum. For D6 it is maximum, and for D5 and D10 it is minimum. That is 0. That is, you can say, 0 value. If you want to see understand John Taylor distortion, then you can also understand that also. See, John Taylor distortion also we can understand, okay, so that is by looking its configuration or electron are arranged in EG and T2G orbitals. So tomorrow we will going to take John Taylor distortion, and also you can have a which in which case you are getting strong on distortion and in which case you are getting weak distortion, and we will also see the molecular orbital theory. This is the crystal field theory. Then we go for molecular orbital theory and types of structure. It may be spinal and all this structure, and also see how you can calculate wavelength using CFSC. So that application also we will going to check tomorrow. So now we stop here. Thank you very much.
Sir,
Yes.
tomorrow classes will be started from 9 a.m.
What you are saying?
कल
कल जो आपका क्लास है वो 1 to 9 बजे है मॉर्निंग में.
Yes, sir.
And second one is in afternoon. It may be at 1 o'clock or.
Sir, 8 to 9 या 9 to 10?